Okay, ladies and gentlemen, welcome back. Good afternoon, good morning, or good evening, depending on whenever you're seeing this. What we're going to be discussing in this lesson is how we are going to kind of look at a graph of a rational function and work our way backwards in order to write the equation of it. So what we had been doing prior to this is we had an equation of a rational function, and we broke it down by simplifying it to see the polynomial in the numerator and the denominator, what it would be in factored form. So that way we could identify any roots that the function had or any vertical asymptotes that the function had. And then from finishing going through the Schrade process, we were able to graph a rational function without the use of a calculator or without the use of a graphing calculator. Well, what we're going to be doing in this lesson is kind of the opposite side of that coin, where you're going to be provided with the graph of a rational function, and from the graph you'll have to identify certain key points that will then allow you to write the equation of that function. And what you're seeing here on this screen is probably two of the more important things that you're going to be working with when you're trying to write the equation of a rational function. You want to know what are the roots. Remember, the roots come from the numerator of the rational function. So we want to know, where does the graph touch the x-axis? So that's why here it's telling you we want to first be able to identify what are the x-intercepts. And of course we want to know, by looking at the graph, does it cross the graph at the x-axis, or does it touch the x-axis and then bounce off of it? Because that will tell you if the root has a multiplicity of 1 or a multiplicity of 2. Same thing here with the vertical asymptotes. The vertical asymptotes, remember, come from the denominator of the rational function. And at this point, again, we want to identify, at a vertical asymptote, will a function come together or not? If the function comes together at a vertical asymptote, it means that the root repeats in the denominator, indicating that it has a multiplicity of 2. And if it doesn't come together at the vertical asymptote, it means that the roots don't repeat, so each of the roots would have a multiplicity of 1. So here is the first graph that we're going to be looking at. Now, in your notes, you might want to just pause the video at this point and get yourself a nice sketch of the function that you see here. It doesn't need to be perfect, but we need to be able to identify certain key points. So the first thing that we want to know, remember, any function that we have, let's kind of look at it like this. And since the graph is blue, let me pick a different color here, so that way what I'm writing doesn't consist with the color of the graph. So let's call this function f. Okay, in a rational function, the roots come from the numerator and the vertical asymptotes come from the denominator. So the first thing I want to know is, what are my roots? And looking at the function that we see here, we have a horizontal asymptote here, which is at y is equal to 1. And because the horizontal asymptote is not 0, we know it's not a bottom-heavy function. So we should know when we've finished with our function, it should be a balanced function, meaning the degree of the polynomial on the top and the degree of the polynomial on the bottom should be the same. And I have a vertical asymptote here at x is equal to 4. I have a vertical asymptote here at x is equal to -6. And here's what I really want to start with, is I have my root. Here I have a root at x is equal to -2. And looking at the graph, it doesn't touch the x-axis at any other place. So there's only one root. Now, the thing about this root is that the portion of the rational function in between the two vertical asymptotes, it only touches the x-axis at one point, and then it bounces off of it and turns back around. So that means this root is tangent to the x-axis at x is equal to -2. So I have my roots here. I have a root at x is equal to -2 and it's tangent to the x-axis because it just bounces off of it. So the factor that would give me the root of x is equal to -2 would be x plus 2, and because it is tangent, it must have a multiplicity of 2. So the next thing I want to look at, where are my vertical asymptotes? Well, we've already established by looking at the graph that I have a vertical asymptote at x is equal to -6 and at x is equal to +4. So the factors that produce those particular vertical asymptotes would be x plus 6 and x minus 4. So this part right here is the numerator, and this part right here is the denominator. And we can take those two parts and write our function, and we'll kind of leave it in simplified form. X plus 2 squared over x plus 6 times x minus 4. And here is our rational function. And this would be kind of in simplified form. If you wanted to, you could multiply everything out in the numerator and the denominator, so that way both parts of the rational function would be in standard form, but it's not necessary. We'll just leave it at that point right there. So let's take a look at our next example. Again, pause the graph at some point, or pause the video at some point, so that way you can get a decent copy of the graph into your notes. All right, and again, let's call this function h. So basically every rational function follows the same thing. My roots come from the numerator, my vertical asymptotes come from the denominator, and so looking at the graph, those are some of the things that I really need to identify. All right, so let's look at our roots first. I have, looking at the graph, it touches the x-axis one time here, and it's still hard to see, but you can see it. There's a little white space in between the blue graph and the x-axis, so that tells me that it goes through the x-axis there, and it also kind of touches the x-axis here, and it also goes through the x-axis. So I have two roots, and because they both go through the x-axis and are not tangent to it, both of those would have a multiplicity of 1 as a factor. So I have a root at x is equal to, that looks like about to be -1, and I have a root at x is equal to a +2, and so the factors that would produce that would be an x plus 1 here and an x minus 2 here. So now let's look at my vertical asymptote. The vertical blue line that you see here is my vertical asymptote at x is equal to -3. So looking at it, the graph itself, the left side of the graph and the right side of the graph, as they come together, or as they come towards the vertical asymptote, they both go up. So that tells me that they come together, the left side of the graph and the right side of the graph come together at the vertical asymptote. And because they come together, that tells me that the vertical asymptote as a factor has to have a multiplicity of 2. So I have a vertical asymptote at x is equal to -3, and it comes together there. So the factor here is going to be x plus 3, and because it comes together, it has a multiplicity of 2. So we've identified the roots, we've identified the vertical asymptotes, and all their multiplicities. So my final function is simply going to be, in the numerator, x plus 1 times x minus 2 over x plus 3 squared. And that is our final function. Now again, if you felt the need to, you could multiply out the numerator and the denominator, so that way both parts of the fraction would be in standard form, but it's not necessary. In fact, it would just be easier to just stop there and leave it as it is. Okay. Now the last thing that we're going to be talking about, part of your homework assignment, is going to ask you to be looking at graphing a function that has a what we refer to as a discontinuity or a removable discontinuity. That means essentially there's a hole in the function. The H in the Schrade process, if you recall, stands for a hole. A hole comes from after we simplify the rational function. If there's a factor in the numerator and a factor in the denominator that are common, they simplify to be 1. So that essentially tells you that I should have a root and a vertical asymptote at the same place. And that's not possible. If a function is undefined at a certain point, I can't also have a solution at the same place. So that's what we refer to the fact that it is discontinuous. There's a hole there. So here is a very simple function that I would ask you to graph. Now, looking at the Schrade process, first thing we want to do is simplify it. We can factor the numerator and the denominator. So if I factor the numerator, that is the difference of two squares. So I'd get x plus 4 over x minus, or times x minus 4 over x minus 4. Now the denominator can't simplify. But if you notice now, we have a factor, the x minus 4, that is common to the numerator and the denominator. So the final simplified function is simply x plus 4, which if you just graph x plus 4, that's a line. Okay? But because I have a factor in the numerator and the denominator that are shared, that tells me that I have a hole and I have a root and a vertical asymptote at the same place, which is not possible. So that tells me that there is a hole at some point. So to identify where the hole is, I'm going to take the factor that is common to the numerator and the denominator, which is the x minus 4, and I'm going to set it equal to 0. Solve for x. So the x coordinate of my hole is when x is equal to 4. To find the y coordinate of the hole, I'm going to take the 4 that I got here and put it into the simplified rational function, which is just x plus 4. So if I put the the x coordinate into that, we can now find what the y coordinate is, which would be 4 plus 4. So the y coordinate of my hole is going to be 8. So the coordinate of my hole is at 4, 8. Now the simplified function, x plus 4, that is a relatively easy thing to graph. It's just a linear function. So my y-intercept is at a positive 4. My slope is a positive 1. And we can now identify where the hole is going to be, which would be at 4, 8. So 1, 2, 3, 4, 3, 4, 5, 6, 7, 8. So here's my hole. So what we would have is a function that looks like a straight line, but we have to have our hole identified here in the function. Now, if you were to type this particular thing into a graphing calculator and say, what does it look like when you graph it, the graphing calculator wouldn't show you a big hole right here at 4, 8. It would look like a straight continuous line. But now the last thing that it's not asking you to do here, but it does ask you to do it on your homework assignment, if I recall correctly, is it basically says write a piecewise function that would fill in the hole, meaning so that way there's no gaps anywhere in the function when we graph it. So the way that we would do that, so here we're calling this function p, so I'm going to say p of x is equal to, and the way that we would write the piecewise function that kind of fixes that whole problem is I'm going to take I'm going to move this over here because I'm not giving myself enough room. So we would say p of x I'm going to take the original function that they gave us, which would be x squared minus 16 over the x minus 4. And that says we could use all real numbers except x cannot equal a positive 4, because that's where my vertical asymptote would come from. And if I put a 4 into the denominator, that gives me 0, it makes it undefined. So what would I have to do in order to fill in that hole there? Well, we would have to have a straight line where y is equal to an 8. Because if I have a horizontal line that at y is equal to 8, it'll go through that hole there. But all I want to have for that one is I don't want to use every number. I only want to use the one number that I need for my hole. So the graph itself is one thing that we would be doing, and writing a piecewise function to kind of plug the hole is what we would kind of finish things off with. So that's essentially it for that particular lesson. Again, we want to identify the roots and the vertical asymptotes of a graph to see how we could put together a equation for a piecewise or for a rational function, and identify uh, a discontinuity, or more commonly called a hole, in a rational function, and uh, identify a way of plugging a hole with a piecewise equation. So that's about it for today. Make sure that you have any questions that you have from watching this video written down, so that way you can come see me in class about it, and we'll see you soon.